So this first scenario is discussed in Gujarati and Porter, primarily I think from a theoretical rather than a practical perspective. So the situation is that the error variance is proportional to x squared, and really I think the spirit of this is you shouldn't take the equations too seriously. All it's trying to do is represent the situation where the error variance increases as some of the x variables become large. So for instance, if you start with this first model here, y equals beta 1 plus beta 2 x2 plus the error term, the variance of the error term is then proportional to x squared, so you haven't got homoscedasticity. Then if you divide through by the square root of the offending x term, because the variance is a quadratic operator, then yi divided by xi is then expressible in the form beta 1 over xi plus beta 2 plus ui over xi, and the idea would be that in this case the term ui over xi would now be an error term with constant variance. And then the idea would be that you could then estimate this final equation on the slide by the ordinary least squares regression approach. Okay, so I suspect this is primarily of theoretical rather than practical importance, but the thing it's trying to abstract from is the variance increasing as when the x increases. Second example discussed in Gujarati and Porter, where the error variance is proportional to x, and it's the same basic way of operating in order to resolve this problem. So what you have to do is again divide by the square root of the offending x term, precisely because the variance is a quadratic operator. So if you start with this first regression model on top of the head, so y equals beta 1 plus beta 2 x2i plus ui, so this is again a two-variable regression model, but in this case it's assumed that the variance of the ui is proportional to x, so you haven't got homoscedasticity. So divide again through by the square root of the offending x term, so in this case just divide through by square root of x, and then in this case what you have is yi over square root of x is beta 1 over the square root of xi plus beta 2 square root xi over the square root of xi. So what you have in this case is a regression equation with the ui over square root xi term. So you can estimate this by ordinary squares, but what you would have to do in this case is estimate it without an intercept term. So that's quite an unusual regression model to consider, and as part of this I think this does reinforce that this is primarily of theoretical rather than practical. So another example discussed in Gujarati and Porter is weighted least squares. Now in the days when people sat exams, I've described this as non-examinable. So in rare circumstances you may encounter heteroscedasticity and know the exact form of the heteroscedasticity that can occur. Now if this happens, there's some underlying mathematical theory involved. The only example of this I've seen is using a weighted least squares approach to estimated a generalized linear model, actually a logistic generalized linear model. So as far as this example goes, since generalized linear models can now be fitted using specialist modern software, there's no need to use an approximate approach based on weighted least squares. So I'm afraid I can't help but think weighted least squares has limited importance for this course, though it is a clever idea and certainly is of historic interest, but I think now with modern methods and modern software it's becoming less and less relevant. Okay, and I think that's certainly the case with R, because R has this online user community and there will be progressively more and more code written to incorporate new and more advanced models. Now, let's go through a little bit numerical tests for heteroscedasticity. Now, I said before, it's important for two reasons really. Firstly, I think it's one of the few examples that you see where eViews is demonstrably better than R, probably because this is a specialist econometrics topic rather than a sort of generic statistical topic. And the other thing I ought to say is that this is probably one of the few examples that you're likely to see where the graphical tests are actually more important than the numerical tests. So it's easy, I think, to sort of think from a student's perspective that numerical tests give you more precision and more precise, easier to interpret, and I've got some sympathy with that point of view, but again, I think this is one of the few scenarios where actually graphical methods are preferable. So the two methods that we will discuss in this course are the Goldfeld quant test and White's general heteroscedasticity test. Now I've described them there as both non-examinable. So this was true in the days when people could sit physical exams. They're only going to be of tangential interest on this course, partly because their use relies on eViews, and eViews software is rather difficult to access on these days where we haven't got consistent access to the physical campus. So the Goldfeld quant test, so this is designed to sort of test this sort of specific case of heteroscedasticity. So the idea is that the variance might increase as one of the x variables increases. So this is an example of this in equation 8. Now, equation 8, I would suggest you don't sort of treat this as literally as it appears on the slide. Really what this is trying to articulate is a scenario whereby the variance increases as one of the x variables increases, and this is just a common way of writing down something that's a neat form that would display this behavior. Okay, I don't think it's necessarily to be taken too literally that this variance is proportional to the square of the x value. It is just really meant to articulate that the variance might increase as some of the x variables increase. Now, how this is sort of phrased statistically then, you start with a null hypothesis of homoscedasticity, and the alternative hypothesis is that the variance in this case is proportional to the square of the x variable. And again, rather than a precise mathematical equation, this is just meant to articulate the idea that the variance might increase as the x value increases. So the Goldfeld quant test is discussed in Gujarati and Porter, and really for our uses today does necessitate eViews. So this is of only tangential interest to this course this year. So the idea would be that you begin by ranking the observations according to the values of the xi from smallest to largest, and the central C observation and sample into two groups. So you've got one sample of large x values and one sample of small x values, and essentially what you're trying to do is test for a difference in variance in both segments of the sample. In order to do this, you need to sort of take out the central C bit of the sample. So the idea would be that you fit some separate regressions to each segment of the sample, form this statistic, and under the null hypothesis of homoscedasticity, the ratio of the two residual sum of squares should have this f statistic value. If you have large values of the f statistic, this would cause you to reject the null hypothesis of homoscedasticity. Now, it's not necessarily clear in this what the right values of C to take are, but there are some sort of sensible guessed values there. So if n is around 30, take C equals 4. If n is about 60, take C equals 10. Okay, further discussion in the Gujarati. There's an example here of another numerical test, White's general heteroscedasticity test, and this is discussed in Gujarati and Porter, chapter 11. So suppose you want to fit the regression model at the top of the slide. So the idea is that you estimate this equation and then obtain the residuals, and then you would fit an auxiliary regression to the square of the residuals. Look at equation 10, this looks a little bit weird, but it's coming from a sort of quadratic expansion x3i, so there is some underlying mathematical structure here coming from a quadratic equation, and it's sort of natural to expect this to be a quadratic because the variance is itself a quadratic operator. calculate the R-squared value for this auxiliary regression, and then use the equation in equation 9 to perform a hypothesis test. And the idea would be that if you have a significant chi-square statistic in equation 9, you would then have formal numerical evidence for heteroscedasticity. So this is primarily of tangential interest for this course, but this is a sort of numerical test that can be run on occasion for heteroscedasticity. So what I wanted to sort of try and get across here is that the subject isn't necessarily guaranteed to be as formulaic as you see when you first encounter things like the T statistics, the R-squared statistic, and the S statistics. So statistics in practical project work is not easy. There's not necessarily any right answers. Alongside that, however, there's various things that students in this class might be able to do better than myself, even though I like to think of myself as a bit of a whiz in terms of math, stats and finance, precisely because there's this need for interpretation and common sense. So the way to sort of proceed here is quite nuanced. If you find evidence for heteroscedasticity, the easiest thing to do is to use White's formula for heteroscedasticity consistent variance and the estimated standard errors that go alongside that. That's easy to do in E-views because that's a standard econometrics thing. It's much harder to do in R because this is a specialist econometrics thing rather than a general statistics thing, and this would typically result in larger estimated standard errors than the usual regression approach. And the idea then that this would give a more robust, more conservative approach to assessing and estimating statistical significance than the usual regression approach. Okay, but it's possible that you might find evidence of heteroscedasticity and there isn't an automatic solution to it.